Hello to all of you. This is Dr. Dhaval Maheta, and today we are going to discuss about non-stationarity and unit root testing. Stationarity of any series means the series has got a constant mean, constant variance, and the covariance between the different observations do not depend upon time, and it only depends on the distance or the lag between them. Let's try to understand this thing in a very simple way. Say, for example, we are having one series, very simple series, which is straight. Can we predict tomorrow what will be that? What will be the value? Yes, definitely, because the series is having a constant mean and the variance is also constant. Can we predict this series? Yes, we can predict this series also because the variance is constant. Can we predict this series? Yes, we can predict this series also because variance is constant. More or less, if we differentiate this series, the mean will also be constant. Moreover, it has got one feature, it is a mean reverting series. Now, if I talk about the series, can I say mean and variance is constant? No, I cannot say because for the different time interval, the means go on changing. Moreover, the variance also changes. And therefore, this is a non-stationary time series. Non-stationary. These are all stationary time series. Now, there are some features of stationary time series. Let's try to understand. I'll give you an example of ECG, that is a cardiogram. Must have all seen this. Series is having this type of pattern. The feature of this series is that it is a mean reverting series. Mean is constant. Moreover, the variance is also constant. Spread of the data is also constant. Another thing which is most remarkable is that if I take the covariance of these two observations, say for example, these observations are y I and y. I calculate the covariance between these two. Similarly, I take the covariance of another two, yk and yl. And if I compare this, the covariance will be constant. Now let us try to understand the same thing with the help of definition. Let us go in the definition. The stationary time series has got the constant mean, constant variance, covariance between yt plus j is equal to covariance ys plus j, it is constant. The basic difference between stationary and non-stationary time series is that the shocks are temporary in stationary time series and over the time the effects will be eliminated. But in case of non-stationary time series, the shocks are permanent. It means that non-stationary time series will depend on time, which leads to that it does not have any long run mean to which the series returns. There is no long run mean. And the variance will depend on time and will approach infinity as time goes to infinity. So for better prediction, we always require the series which is stationary. And therefore, our efforts will be to make the series stationary. Now we'll have to understand the first order autoregressive scheme, that is yt is equal to 5 yt minus 1 plus ut. So my today's observation is dependent on yesterday's observation. Today's weather is dependent on yesterday's weather. Today's stock prices are dependent on yesterday's price. What will happen if phi is less than 1? Say for example, if this takes the value less than 1, 0.9, So you can say you will be getting a series which is stationary. If phi is greater than 1, then the series will explode. The reason for this is, let's try to understand in a very simple way. Phi is equal to 1. Say for example, the yesterday's share prices were 1000 and every day it is increasing by 1.1 times. Just imagine that what will be the share prices after some. So it means that the series explodes. Many of the theories does not fit in this case where phi is equal to phi is greater than 1. What is the thing when phi is 1, phi is equal to 1? This is a clear-cut example of AR1 model. As first difference, when we'll take the first difference, the series will become stationary and we'll be able to work on this series. Interpretation of phi. When phi is 1, the series is non-stationary and it means that the shock never dies. When phi is greater than 1, series explodes, which means that any shock given to the system propagates and increases with time, which never happens. Here, small correction there. To make this series stationary, we will have to take first difference. So I was talking about as first difference of this series is stationary, not the base series. Okay. When phi is less than 1, the shocks to the system gradually dies away. And so the theories fit here very well. Here, the theories don't fit. The first order autoregressive scheme is phi t is equal to phi yt minus 1 plus ut. If I take phi is equal to 1, differentiate yt minus 1 from both the sides, then I get delta yt, which is equal to et. So it is a white noise process, and this series is stationary. Therefore, after first differencing, we get the stationarity in the series. Now, how many times the series has been differentiated? On that, we will name it as order of integration of series. So if I take two difference of the series, then it is a series integrated of order of 2. Normally, we should not differentiate any series more than 2 times. Now, why it is necessary to carry out to check the stationarity in data? Many times we get the spurious regression. This means that we get a very high values of r square and a significant f value. That is jointly this all these variables are contributing towards jointly all these independent variables are contributing towards a dependent variable. But when we check individual coefficients p value, they are insignificant, and therefore it is a clear-cut case of spurious regression. Second thing is the Durbin-Watson r square will be greater than the Durbin-Watson statistics. To make the series stationary, there are two methods. One to take the log transformation, and another is first differential. How to identify that this is a spurious regression? So Granger and Newbold in 1975 proposed that if R square is greater than Durbin-Watson, or if R square is very much near to 1, then the regression must be spurious. Now there are some properties of the stationary time series. One of the properties, if x and y are stationary, then any linear combination of x and y is also stationary. If x and y are stationary, then error in them will also be stationary. So we will have to check the series at base. If it is stationary, then we will say it is a I0 series. We take first difference, that is I1, and if it is stationary, we will say that it is if we take first difference and if the series is stationary, then the order is I1. If still the series is not stationary, and if we take the second difference, then we will say the series is of second order. Very simple example, a mathematical example. Let us try to understand this thing by using mathematical function. Y is equal to x cubed. If I take the first differentiation, dy by dx is equal to 3x squared. This is known as the series first order series because the differentiation has been taken off first order. If I say d square by dx square, so now it is 6x. So it is I. Okay. Now we will have to test the series in all the three conditions. That is, it is having constant, no intercept, constant and intercept and trend. There are three ADF equations to test whether a particular time series data is stationary or not. All these three must give the same decision to come to a decision, whether a particular time series is stationary or not. So the Decker-Foley test was given in 1979 and 1980. They devised a procedure to formally test for non-stationary. Key insight of their test is that the testing for non-stationarity is equivalent to testing for the existence of unit root. Now, what this concept is, let's try to understand. Yt is equal to phi, yt minus 1 plus ut. Phi is equal to 1. Then obviously the null hypothesis is if y is equal to 1 or the alternative is phi is less than 1. We cannot have phi greater than 1 because we have seen that the series will explode in such scenario. Now subtract yt minus 1 from both the sides. What I get, delta yt minus 1 is equal to phi minus 1 yt minus 1 plus ut. So now I will give the name gamma. Phi minus 1 is gamma. What's the relationship between phi and gamma? Phi, and the null hypothesis is gamma is equal to 0, which means that phi is equal to 1. The original series is non-stationary. The first difference is stationary. If I talk about alternative hypothesis, gamma less than 0, phi less than 1, series is stationary. The original series is stationary, and the first difference will also be the stationary. If I say gamma greater than 0, phi greater than 1, series explodes and the series is non-stationary. We'll have to test the series on all these three equations. Yt is equal to delta yt minus 1 plus ut, that is a random walk. Yt is random walk with drift. We are including a drift here, that is beta 1. Yt is a random walk with drift around a stochastic trend. So beta 2 t plus delta yt minus 1 plus. So we will have to test on all these three conditions. So let us see how we can do this in EViews. So I'm using this data frame, capital, employment, GDP. I'll go in view, graph. Click OK. And you can see the series. Now from here only, you can monitor. Okay. Let us see what happens if I take the first difference of this series. What happens if I take the log of this series? What happens if I take the log difference of more or less log difference will solve our problem. It's to make the series mean reverting. Now there is a graphical method to test the stationarity, and the method uses correlogram. It's a simplest test of stationarity based on autocorrelation function. Basically, or any autocorrelation function is covariance at lag k divided by variance. So if we plot delta k against k, we get the graph which is known as population correlogram. Since here we are dealing with the sample only, so it is known as a sample autocorrelation function. Formula is sample covariance divided by sample variance. Now how to generate correlogram? View, correlogram, add label. It will ask me the labels, legs. Basically, the rule of thumb is that number of observations divided by 3 are the legs to be. But it also depends upon is your data daily, monthly, or yearly. You can just click here, OK. First of all, you will have to see the p-values. All the p-values are less than 0.05, and therefore we can say that the data is non-stationary. Moreover, other observation is that these spikes are beyond the control limits plus or minus 3 sigma, and therefore they are all significant. This is also significant, and therefore data is non-stationary. Now the same thing we can carry out with the help of unit root testing. View, unit root test, label, intercept. Click OK, and we have got the values. You can copy this in word file. You have to see this p-value and see the null hypothesis. GDP has a unit root. The null is GDP has a unit root, or in other words, data is non-stationary. The alternative is GDP does not have unit root, data is stationary. There is a small change which we'll have to do. The test which is conducted is Phillips parons. First of all, we will do with augmented decay Fuller. So we'll go back here and the change is to be done from here. Augmented decay Fuller. Click OK. And again, copy this. OK. Phillips parons we will do later on. Now you will have to see these values. The null is GDP has a unit root, or the data is non-stationary. The alternative is GDP does not have unit root, data is stationary. You can see the p-value here. As the p-value of this test is 1, which is more than 5% level of significance, we fail to reject null hypothesis, which means that the data is non-stationary. We'll go back again here, view, unit root test. We have tested for level, keep it as it is. Now test it for trend and intercept. Click OK. We'll get the same results. Again go back, view, unit root test, and none. Click OK. You get the same result. Now you carry out this test at first difference. First of all, let us see are we getting proper results in parallelogram or not. So for this, you go in view, parallelogram, and now make this first difference. Click OK. All the p-values still are less than 0.05 and still the data is non-stationary. We can confirm this thing with the help of unit root test. Again go back, view, unit root test, change this to first difference, click OK. Again, the p-value is more than 0.05 and therefore we fail to reject null hypothesis. This means data is non-stationary. We can test again, keeping all other things constant. Keep first difference as it is. Now check for intercept. Same, the result is same. Again go back, view, unit root test. Now trend and intercept, click OK. Here, we are able to reject the null hypothesis. But the thing is, there should be a confirmation coming from all the three. That is intercept, trend and intercept, and none. Now let us try to carry out this same test using second difference. View, parallelogram, second difference, click OK. And you can see most of the p-values are more than 0.05 and therefore the data is now stationary at the second difference. Let us confirm this thing with the help of unit root test. View, unit root test, second difference. We'll start with intercept. Click OK. You can see here the p-value is now less than 0.05. We can copy this here. Copy. We'll take this into the Word file. Control V. So I'll copy this also. I'll write the interpretation. So the p-value here is less than 0.05. So as ADF test, as p-value of ADF test is 0.0012, which is less than 5% level of significance. So we reject null hypothesis. We reject null hypothesis, which means that the data does not have unit root and data is stationary or the series is stationary. Let us go back. Again, view, unit root test. Keeping the second difference as it is, now we'll have to check for trend and intercept. We got the same result. Quite good. View, unit root test. None. Click OK. So, from all the three ADF equations, we got the same result that the series is stationary at the second difference. We can also use another test like Phillips-Perron's test. Phillips-Perron's test is used normally when we are having structural break in the data. So whenever there is a structural break, meaning any change in policy or any sudden drift in the graph, then we are using Phillips-Perron's test. Or in other words, augmented Dickey-Fuller is, you can say, the parametric test, and Phillips-Perron's is non-parametric test. When the series is normally distributed, use ADF. When the distribution is not known, we use Phillips-Perron's test. Then there is a Phillips-Schmidt-Sin test, that is a KPSS test. And here the null hypothesis is a little bit different. Here say Y is stationary. It is reverse. You have to remember this. Our null hypothesis in case of KPSS test is our series is stationary. Now let us carry out the same test on our data. Let us go back. View, unit root test, and this time change it to Phillips-Perron's. And you can keep second difference as it is, intercept, click OK. We got the same result. Again, go back, view, unit root test, trend and intercept. Here, again, the p-value is less than 0.05. We reject null hypothesis, which means that data is stationary. View, unit root test, and this time take none, click OK. Now, we want to carry out the KPSS test. Remember, in case of KPSS test, our null hypothesis is reverse. That is, the series is stationary. View, unit root test, KPSS. Again, keep this on second difference, intercept, check it. Now, you have to see here the p-value. Now, how to interpret this? Let's try to understand. This is the KPS statistics which is calculated for your series. And this is the standard values. So, when your test statistics values are less than the critical values, we fail to reject null hypothesis. Our null hypothesis is data is stationary. Again, repeat. When the KPS statistics values are less than critical values, we fail to reject null hypothesis, which means that our null hypothesis data is stationary. If this value is more than this critical values, we reject null hypothesis and data is non-stationary. Now we very well know that the series becomes stationary at the second difference, but we will have to generate this series in EViews. So for this, how to generate the series? Let's try to understand. When generate the series by the command generate, I'll say dgdp. This is just a name. I can give any name here. So I'll say dgdp, difference of 1. And you can see the series has been generated of first difference. Similarly, I can generate the series of second difference. Generate dd gdp, d gdp, comma 2. Enter. I'll get ddgdp. Now what actually happens when we take the first difference? Let's try to understand. Open all the series one by one. Open as. So this is 11,000. This is 1,14,000, 1,20,000. So when I take the first difference, it will take the difference as 1,20,000 minus 1,40,000. So 6,367. 1,29,000 minus 120. So 8,777. When I take the second difference, it will take the difference of 8,777 minus 6,367. Now for every difference, you can see the observations which we have to surrender, or rather, there is a loss of information which is happening. When we did first difference, we have lost the one observation. When we take second difference, we have lost two observations. Normally, it is not recommended that you go for more than two differentiation of the data. Now, one method is to get the series stationary is by taking the first difference or the second difference. Let us see the series which we have generated, that is by second difference, is it stationary or not. We'll activate this series, view, parallelogram. Now this becomes the base series. Understand, friends? Now this becomes a label because we have already differentiated for 2 times. And now if we take second difference, it will be 4 times different. So make it sure we keep it at label. Click OK. We get the same result. Again, go back, view, unit root test. Make sure you activate the augmented decay fuller. And here, second difference should not be there. Label. Click OK. You get the same answer. Now, there is still another method to make the series stationary, and that is by using log. So here, generate LGDP, that is a log of GDP. Enter. So a new series will come into the existence, which is a natural log of the existing series. View, parallelogram, keep it at level only, click OK. So even after the first difference, even after taking the logarithmic transformation, the series still has got some spikes. This we can confirm by with the help of p-value. P-values are less than 0.05, which hints us that this series is non-stationary. We can further confirm this by using a unit root test, label, intercept, click OK. The p-value is more than 0.05 and therefore we fail to reject null hypothesis. Null hypothesis is that the series has a unit root, data is non-stationary. I can further go and I can also take the difference of this series, generate DL GDP, that is D LGDP, comma 1, enter. And I'll get the new series, that is the log differentiation of the series. Let me see. View the parallelogram. Give it label only, click OK. So the DLGDP, that is a first difference of the log transformation series, stationary. Let us confirm this thing with the help of unit root test. View, unit root test. Keep things as it is. Okay. And you can see the p-value. It is less than 0.05. For more videos on econometrics, kindly subscribe to my channel. You can follow me on LinkedIn and Twitter. Thank you.